Okay, we are now forging ahead into the second big topic of the term, which is digital imaging. So that covers images and photos, or really anything visual that we see that's not moving. So again, it's the second of our big four topics: audio, images, video, and interfaces. Um, and so we're switching gears to change from sound to vision. But we're going to find that the foundational concepts are very, very similar. That of course, we're going to be talking about things like sampling and quantization, which will have an impact on how we see things. Um, but of course, now we're talking about a different domain, right? Not the domain of air and sound pressure, but the domain of light and how we perceive light. Once again, we'll be informed by our human physiology, how our visual system works, and that will then lead us to methods that we can use to represent images, compress them efficiently, and we'll learn about how those different formats work and how they differ and when to use which one. So let's return to a topic that, of course, we're very familiar with, and that is frequency. Right? So in sound, of course, I defined frequency as the inverse of period. That period was something about how long it took for something to repeat, and then frequency is the inverse of that. Um, you can also think about frequency, whether it's sound or any other medium, as this, that frequency is the speed of propagation in a medium, right? So which we often represent by c, divided by the wavelength, right? The wavelength in meters. So c we usually express as a velocity, meters per second. So the speed of sound, for example, is about 300 meters per second. And so you can actually compute wavelengths for sound as well in meters or fractions of a meter, or sometimes they really are meters long. So when we're talking about light and images, um, some of the units or some of the standards that we use to represent things in images are slightly different. So frequency is still very much in hertz, right? Cycles per second. Wavelength is a measure of distance, so we'll use meters for that. But now the critical factor in imaging, right, is c, the speed of light, or really the speed of electromagnetic waves, which is about 3 times 10 to the 8th meters per second. It's really, really fast, right? 186,000 miles per hour or so. So it's helpful to think about variations in light in terms of wavelength and frequency. So let's take a look at a very different kind of spectrum that we're used to, than what we're used to from previous lectures, and that is the electromagnetic spectrum, right? This is the spectrum of electromagnetic energy, electromagnetic waves, including light waves. And this runs a huge range of wavelengths and thus frequencies, right? So on frequencies, on the one side here, you're seeing, well, 10 to the 5th here, and all the way 10 to the 21st here. Correspondingly, because it's the inverse of wavelength, you're talking about really, really tiny wavelengths here, 10 to the minus 12th meters, right? That's quadrillionths of a meter, I think, up to thousands of meters here in wavelength, right? So, and of course, you can see that that spans the range of rays that, again, you may be familiar with, from gamma waves up to radio waves. X-rays are down here, and then this range, ultraviolet to infrared, right? And if we zoom in just on this tiny piece here, this little bit in between the infrared and the ultraviolet, that is the visible spectrum of light. That's the energy that we can see. And you can see if we zoom in on that, that spreads out across here a range of different wavelengths, right? And they're all pretty small, right? But across this different range of wavelengths and thus different frequencies, we see different colors, right? And violet from one end to red on the other. Again, you may recognize this order, maybe as red, orange, yellow, green, blue, violet, right? So that's the order of the rainbow going this way. And then this way, in this direction, that's where we find the ultraviolet or beyond violet. And then on this side, we have the infrared or less than red in terms of frequency here, right? Or under red, I guess is what that means. So the visible spectrum, the things that we see as light and color, are a really, really tiny portion of this much larger electromagnetic spectrum, right? But the key point that I really want to emphasize here is that our eyes, right, are turning different frequencies of light energy, of electromagnetic energy, into a color, right? Or that's how we perceive it, right? So if we want to recreate a very, one of these colors very precisely, um, we then have to create that light frequency, right? And again, there's a lot of different colors here, a lot of variation. The notion I'm trying to get to here is, right, there's a huge, even in this tiny little piece there's a really, really broad range of colors that we perceive. So does that mean we need a way to generate all of those different frequencies individually? Or maybe are there some kind of building blocks for different colors, different combinations of light that then we can turn into different colors, right? So kind of like in audio, we have the building blocks of individual sinusoids that add together to form different sounds, different timbres, right? Can we do the same thing with visible light and with colors, right? Because it would be maybe potentially very challenging to create something that can generate all of these different frequencies very precisely to be able to generate all those colors, right? So let's take a little closer look at this, right? So I'm zooming in on just the visible range, and you can see that, hey, there's sort of the bluish part here, the greenish part here, and the reddish part here, right? And maybe you know already that red, green, and blue are particularly important when it comes to images, right? And you may have heard that in terms of RGB, red, green, blue, displays or monitors. So what's particularly important about that? Well, it actually goes back to then human perception. So this is a slide I've returned to many times throughout the term. And again, the difference and the distinction between the physical things that we can measure and how we perceive those. So this is the same slide I've shown before in terms of hearing, right? That the things that we measure in a signal, frequency, amplitude, power, have a relationship to the things we perceive, pitch, timbre, and loudness, right? Well, now let's switch to the visual domain, right? Again, we're going to have properties that we can measure from a signal, an image signal here, that then we are going to perceive as changes in color or brightness or texture. It's still not a really simple relationship. So let's learn a little bit more about how we see. I'm sure you're somewhat familiar with your eyes and the anatomy of the eye a little bit. Really, the key part here for this class is what we see on the retina, right? Right. The light comes in here. It gets focused by the lens of your eye, and then that light then hits the back of your eye, the retina, right? But what's on the retina, right, is a bunch of highly specialized cells here that we that have evolved to sense different types of light, right? Some of them are designed to sense intensity, so brightness in particular. That's highlighted in the black cells here. Those are rods. They see the world in black and white, just bright and dark, right? But of course, we see the world in color, right? Or most people see the world in color. And in fact, humans are what we call trichromats, 3 color sensing, right? Hence the different colors of red, green, and blue cells up here, right? All along the surface of the retina. So why red, green, and blue? Well, it turns out that these special kinds of cells we call cone cells. Cone cells come in three different sizes, small, medium, and large, let's say. But each type is particularly sensitive to one of those colors, red, green, or basically red, green, and blue. So that's why humans are trichromats. We have three of these types of cells. There are other types of animals, mammals, that are dichromats, where they have two kinds of cone cells. And then there are even some animals, some species that are tetrachromats. They have four types of cells. And there are certain species of birds and fish that have receptors, special receptors for ultraviolet light. That's sort of the fourth area, right? So does this mean we have three kinds of cone cells, right? And one type of cell, the rod cells for intensity. Does this mean that we can only sense three colors? Well, not really. Obviously, we see the world in many, many more colors than that. But if we look at the sensitivities of those different kinds of cells on your retina, the cone cells, and small, medium, and large, right, we see that the small ones are particularly sensitive to blue. This is how they respond when they get hit with blue. But they also respond to some other frequencies, right? Not as much. Right? Likewise, the medium size peak around green, right? And then the large ones peak around orange, or even, picking up a lot of the red here. So it's really not just the response from one type of cell. It's the response when you combine them all that allows us to see those different colors, right? So again, we don't have specialized cells for all these different frequencies. We have three kinds of cells that when you combine them together, give us this bigger picture or broader picture of the range of colors. So if you haven't guessed already, we're going to take advantage of that. We're going to really take advantage of that in how we then capture images and display images, right? Because what this is telling us is that if we can put out the right combinations that are kind of tuned for our cone cells, we can then create almost any color that we want. Right? So that is the principle, right? The cones and the types of cells in our eyes are the principle behind the red, green, blue RGB color space. The idea that if we mix certain amounts of red, green, and blue, we can then create other colors here, right? So you can see how they overlap, and then of course, if you have them overlap maximally, you have all red, green, and blue, then you're going to get something that's very white. But if you mix them in equal proportions, right, but not at full intensity, you're going to get various shades of gray as well. So we mix these three different light sources, and this is what we would call additive color. Additive color in that we start basically with black. If everything is zero, we're at black, and then as we start adding in more and more of each color, we start to then, or more and more of each of the fundamental colors, red, green, and blue, then they add together to form the different colors in the spectrum. So here's kind of a little more of a breakdown of that if you start mixing the red, green, and blue in different proportions like that's what's represented around the outside here, that then you're going to get these different colors along, around the wheel there. And then white, of course, again, is if you add all of those colors together at max, red, green, and blue at maximum intensity. So you may know that initial photographs, the creation of photography was initially black and white. It was only capturing intensity, right? Light versus dark. But obviously, we see the world in color. People wanted to capture color images, and it wasn't until well after the invention of photography that people started to examine how are we going to create color photos. So this example here is from the early 20th century, where this color image here was never actually taken by itself. Instead, three different images were taken in black and white through different color filters. These red, green, and blue, you can sort of see the edge of the filters there. And that by taking an image through a blue filter, a red filter, and a green filter, and then putting those together, then we can create this nice color image here. So this is an image from 1911. The person who pioneered a lot of this basic color theory in photography, his name is James Clerk Maxwell, and he started doing this sort of in the mid to late 19th century. Right? But that sort of became the proof of concept that, oh, now we can take something, that we capture in black and white or per single channel, just one of these filters, red, green, or blue, and then put something that's much more complicated together, right? It has much more color variation than any of the individual colors being represented here, or sorry, than any of the individual color channels being represented here. And this is based on, again, human perception research, right? Now, the existence of cones wasn't actually confirmed until much later, right, in the 1950s. But even before we found the specialized cells, photographers and scientists had figured out that, hey, we're particularly sensitive to these particular sort of component colors, the base colors of red, green, and blue. So we still use this principle today. Let's take a much more modern image, right? So this is a digital image just from a football game. And of course, if you zoom way in, right? If you zoom way in, you can see that the image is composed of individual elements of each a different color, right? But if you zoom even further in, let's say on your display, if you have a microscope or a really powerful magnifying glass, and look at the individual pixels of a screen, whether it's your computer screen, laptop, phone, television, you'll find that those individual elements are actually composed of what we'd call subpixels, right? Partial pixels that are red, green, and blue. And that each of those bigger pixels, one of these squares here, right? And one of those squares is actually a combination of 3 subpixels, right? And that by putting in a certain amount of green, a certain amount of red, and a certain amount of blue, we can turn that pixel into a particular color. Now, just to be completely accurate, different types of display technologies will use different patterns. This is from an old school television, CRT, a cathode ray tube based television. Hardly anybody has these anymore, but these are the super big, super heavy. Used a big glass tube and couldn't still generate very large images. But you can see that each sort of sub area has this pattern of red, green, and blue. A PC-based, a computer CRT, an old style computer CRT might have had a different pattern so that you could have less sort of edge effects between the various regions of the various pixels, the various dots in your image. More modern LCDs have a grid like that, either a rectangular grid, or they might have a diamond-shaped grid like this, where you see different patterns, because it turns out that we're, even within red, green, and blue, we are not equally sensitive to the different colors, and so they kind of weight certain colors a little more by having a few more dots. So that's the essence of digital imaging now, right? We're going to break things down into those component colors, right? So a digital image is a grid, right? It's a grid. In fancy terms, we can call it a two-dimensional function, but every point on that image, right? Every little dot of the image is going to have a coordinate, an X and a Y. And then at that coordinate, we'll call it the function, there's going to be some value, right? That represents either the intensity, if it's just black and white, the grayscale, or the color of the image at that point, right? And of course, if it's a digital image, then those coordinates and the values are going to be discrete quantities, quantized numbers, right? They can't be just any number with an infinite precision around it. We're going to have to figure out some way to turn that into, well, binary values that we can store digitally. So thus, having an image, digitizing an image, will require sampling and quantization, just like with audio, because that's how we get from something that's in the real world, a continuous or analog image, into something that we can represent in ones and zeros. So we're now going to have to talk about two types of resolution in a way. That there's going to be, the pattern of the dots, how closely spaced are they together, sort of the sampling of that. And then, of course, the accuracy of the intensity or the color representation. So the quantization of that value is also going to have, and both will have a huge impact on image quality. So determining the pixel locations for an image is another form of sampling, right? So we're going to take this image that is a continuous space and then measure it, again, at regular intervals, not just across one dimension, but now across two dimensions, X and Y, right? And so that's what's, we're taking this sort of vague pear-shaped image here, here, and then sampling that along this grid, right? The grid now determines the sampling interval. And in this case, we're sampling equally in both X and Y, which is pretty standard, right? And then at each grid point, right, let's say here, right, we're going to measure one intensity value in this case, because it's a black and white image. So, and then to just store that as one discrete number, one discrete point. So if we're talking about just grayscale, shades of gray, usually we'll use 1 byte or 8 bits to create 256 different levels of gray, right? And again, you see a depiction of that in this image below. Now, of course, if we're going to do something in full color, right, certainly the size or the number of pixels that we get is going to matter. In this case, this is a 720, or sorry, an 800 by 720 image. But now, rather than just each pixel being an intensity value, we have to represent a color. And of course, if we do that for the three primary colors of red, green, and blue, or the primary components, then we have to decide how much information is going to be stored in each color, right? And since we use 8 bits for shades of gray, we kind of just apply that to all three colors, red, green, and blue, each of those being 8 bits, right, or 1 byte. So this image, for every pixel or every coordinate point where we've taken a measurement, we actually have 3 bytes, 8 bits of red, 8 bits of green, 8 bits of blue, that 24 bits in total that describe the color at each pixel location. So how does that translate then into the size of an image file, right? Well, similarly to audio, where we would take the sampling rate and the length of the file and then the bit depth, we're going to do essentially the same thing here, except now we don't have just one dimension of values to worry about, we have 2 dimensions. So we're going to have a total of pixels, let's say in this case, capital M columns and capital N rows, right? So a total of M by N, number of pixels, and then multiply that by, so that's the number of pixels, and then multiply that by the number of bits we need per pixel, right? So then your overall image size in bits is just going to be those 3 things multiplied together, right? And I mentioned this just previously, but usually for grayscale, black and white, or shades of gray, we use 8 bits per pixel. For red, green, and blue, RGB, we have 8 bits per color, so 24 bits in total. And then if you want to add other dimensions, like say a transparency or an alpha channel, which I'll describe in the future, that's another byte or another 8 bits. So now you're up to 32 bits per pixel. It's worth highlighting that, so depending on your application, you may be using a number or specifying color in terms of number between 0 and 255, that's 1 byte. Or typically on the web, we specify those colors, those numbers in hexadecimal or base 16, where each digit can be one of 16 values. So instead of just going 0 through 9, we add 6 more values, A, B, C, D, E, F, right? So that each place becomes a value of 16, and that's still 2 places of 16, or 16 squared is 256, right? 256 values there. So Uh, so there are a couple of different standards of how we represent color, and we'll get to that in a future lecture. Um, so there are a couple different ways we can specify those RGB values, whether we're using decimal or hexadecimal. Um, but everything gets mapped to a number between 0 and 255. Yeah. So that's RGB. I just wanted to briefly mention there are different ways of specifying color as well, not just RGB. As we said, RGB is additive, where you're starting with basically a black background and then adding brightness and color on top of that. Well, that's great if you're starting with a black background screen. So what if we're starting with a background that's white, right? Like a sheet of paper, right? So there are different models. In fact, the most common is what's called CMYK, and this is used for printing on paper, right? And we call this a subtractive model because it starts with everything on white and then layering on colors to that will then combine to primary colors that will then combine to create different colors and different shades. So CMY stands for cyan, magenta, and yellow here. So the cyan is sort of the light bluish stuff here. Magenta is sort of the pinkish purplish, and then yellow over here. And then again, now adding those on a white background, they will combine in different ways. When you combine them all together, you see this middle area, you actually get black, or honestly, you get close to black, but then printers discovered that it's really, really hard to get a true black with just those three primary colors. So they added a fourth color. They added a specific black layer, and that is the K, right? Because when they were creating this, K stands for the key plate. The key plate that which was a black plate, that would be added to the cyan, magenta, and yellow layers. So CMYK is very common in printing programs. So if you've worked in any of the publication programs like Adobe Photoshop, it can actually convert an RGB image into a CMYK space that's ideal or better suited for printing. There are other ways to represent color as well. In fact, arguably ways that are maybe a little more intuitive and a little more perceptually aligned with our vision. So, because it's hard to know from, you might have, after a while working with this, an intuitive sense of, oh, I add, 100 of red and 50 of green and 10 of blue, and I get a certain color, right? But that takes a lot of experience. There are other ways of representing the same information. One of those is what we call HSV, or hue, saturation, and value, right? So it holds exactly the same information as RGB or any other color space, but it can be a more intuitive domain, where these three numbers now, hue represents the color, which is a value that will then shift between regions of red, orange, yellow, green, blue, the rainbow pattern, essentially. The saturation is the intensity of that color. You can think of a really, really bright red, or maybe a much darker red. And then the value is the brightness overall, which is also sometimes what I call this HSB, hue, saturation, brightness, but more typically it's HSV, hue, saturation, value. You'll see this as an option in a lot of color pickers on the computer, where you can specify something in RGB, or maybe you can flip to a different tab and see it in HSV as well. So what does that look like? So imagine now this is our color space, color wheel, right? Where as you go around, you can change the hue, right? So, different angles around here are different hues, different colors. The saturation is sort of the intensity of that color. And then the value is a brightness. So that we can change from, a really bright color to something that's much darker or even black there. So if I want to pick a color, let's say, all red. In RGB, that might be 255 red, 0 green, 0 blue, right? In HSV, right, that might be 0 degrees. We usually start here as the 0 degree point. That's 0 degrees because that's straight red, full saturation 1, and a full value, full brightness of 1 there, right? So that gives us the equivalent HSV representation. For something orangish here, which is a combination of 235 red, 130 green, 33 blue, that orangish thing is going to be 29 degrees. So maybe out here, around there, right? Which you can see is pretty similar to that color. And then this sort of purplish thing, which might be 79, 79, 107. This will be 240 degrees. 240 degrees, which is kind of out here. You've got a quarter of the way out in terms of saturation, and then we're going to bring down the brightness to get that duller purple look. So really, HSV is not just a circle, right? HSV is this cylinder, right? So you can imagine the circle. So we're going around the circle to get hue. The saturation is still the radius, but now the value is the height, right? The y coordinate in the cylinder, and you can see that, of course, brighter values are up here and darker shades are down there as well. So lots of ways of looking at color, and of course, a key component of the project will be understanding how you want to try to match color or find things that are similar colors to then create an overall photomosaic image. That's it for this lecture. I'll see you next time.